In this video, we need to talk a little bit more about complex numbers. Specifically, I'll start talking about some of the terminology around complex numbers, and then really work on how we can start combining them, say using addition, subtraction, multiplication, and division. To understand a complex number, you first have to understand what an imaginary number is. And if I really had to describe it, I'd basically say that if you take the square root of -1, you get a number, and that we call this number an imaginary number. Now, just with that simple definition, that the square root of -1 is equal to I, you can actually go forth and express many other types of imaginary numbers just using this. For example, suppose that I had something like the square root of a -7. I could go ahead and express that as an imaginary number. And the way I'd do that is I'd split up the negative sign from the 7, so I'd have -1 times 7, and then take the square root of each of its pieces. Now, the square root of the -1, just from the definition, I would change that part to I. And what I'd end up with is I times the square root of +7. And so I'm expressing an imaginary number that represents the square root of -7. Now, from these imaginary numbers, we can start to describe complex numbers. A complex number is basically a number of the form a plus bi, where a and b are constants, numbers of some sort, and I represents the imaginary part. So what you say is that when you have a number written in this form, that a is said to be your real part, and b is said to be your imaginary part. And in a moment, we'll take a look at some complex numbers, and then start to work to combine them using some of our algebra skills. The good news is, as we start getting into how to combine these, is that complex numbers obey all the usual laws of normal numbers. That means you have the commutative property, the associative property, and the distribution property, just like normal numbers have. So it doesn't matter the order that you multiply them, or it doesn't matter the grouping that you multiply them. So specifically, let's take a look at how you start adding, subtracting, multiplying, and dividing these complex numbers. Let's first take a look at adding and subtracting two complex numbers. When you add or subtract two complex numbers, you're basically just collecting together the real parts of the numbers and collecting together the imaginary parts. One word of warning, when you're subtracting two complex numbers, you have to be very careful on the sign. Let's go ahead and take a look at an example. So here I have two complex numbers, 2 minus 5i plus 1 minus 6i. And in that first number, 2 minus 5i, I would consider 2 the real part, and I would say that minus 5 is the imaginary part. And what I want to do is basically start adding together these two imaginary numbers. Well, I'm going to drop my parentheses and end up collecting together just the real parts. So I've taken the 2 and the plus 1, those are both the real parts. And then I have the minus 5i and the minus 6i, so I've put together the imaginary parts. Now, just like how you combine like terms, you can go ahead and add the 2 and the 1 together to get 3, and you can subtract 6 from minus 5 to get minus 11. And so the answer in this case is that we have 3 minus 11i. And that new complex number represents our answer. So as you can see, that the process isn't too bad. Now, when we do this for subtraction, be very careful on the negative signs. Watch what happens here. Here I have 4 plus 5i, subtract 6 minus 3i. And if it helps when doing a subtraction problem like this, go ahead and put parentheses around that second imaginary number. Now, before I can just drop parentheses, I'll first distribute my negative sign. This will give me 4 plus 5i minus 6 plus 3i. So notice how that minus is on the 6, and minus a minus gives me a positive 3i. Now I'll go ahead and start to collect together the real parts and the imaginary parts. So 4 minus 6 will give me a -2. 5i plus 3i will give me an 8i. And so my final answer here is minus 2 plus 8i. To multiply two complex numbers, you want to think of multiplying binomials. That means you want to say take your first terms, multiply them together, your outside terms, your inside terms, and then your last terms. And so it looks a lot like FOIL. The only extra thing you really have to remember when doing this with complex numbers is that when you take an I times an I, you get I squared, which is equal to a -1. So let's go ahead and give this guy a try. Here I have 1 plus 2i, and I'm multiplying it by 1 plus 3i. I'm going to take my first term, so the 1 and 1, multiply them together. Then I'll do the outside, so 1 plus 3i, multiply those together. Then I'll do the inside, 2i plus 1. So those two multiply, I'll get a 2i. And then I'll finally take care of the last term, so 2i multiplied by 3i. And that will give me a 6i squared. Now you want to go through, now that you got all of your terms for first, outside, inside, last, and combine together what you can and simplify. Those two middle terms will often combine. So here I'll get 1 plus 5i plus 6i squared. And in the last part, you got to take it one step further and simplify the I squared on the end. Since the square root of -1 is equal to I, it means that I squared is equal to -1. So I'm going to swap out that I squared with a -1 and continue to simplify. So 1 plus 5i plus 6 times -1. Well, that will give us a -6 on the end. And we can take that -6 and combine it with the 1, leaving us with a -5 plus 5i. With any type of these problems where you're combining complex numbers, remember that you know you're done when the answer itself is a complex number, that you can clearly see what the real part is, -5, and clearly see what the imaginary part is, the 5. Out of all the operations, the one that's really kind of hard to follow is when you take two complex numbers and you divide them. What makes this a little bit more difficult is that in the division process, we actually multiply the top and bottom by the complex conjugate. Now, if you've never heard of that word before, complex conjugate, it's basically the same as the complex number, but you've changed the sign on the imaginary part. So for example, if you have a number like 5 plus 3i, and you're looking for its complex conjugate, that'd be 5 minus 3i. So watch how this is going to play a part. I want to take 2 minus 5i and divide it by 1 minus 6i. Now in order to carry out this division, I'm actually going to multiply the top and bottom by the complex conjugate of my denominator. So here I'm multiplying the top by 1 plus 6i and the bottom by 1 plus 6i. Now this may look like I'm making things way more complicated. And what I'm going to have to do is fall back on how to multiply complex numbers. So up top, I'm going to FOIL that out and get 2 plus 7i minus 30i squared. On the bottom, I'm also going to FOIL that out and get 1 minus 36i squared. So it looks like I haven't really gotten it, anywhere. It looks even more complicated than what I started with. But remember, you can start simplifying this a little bit more, especially when you have the I squared. Let's go ahead and do that. So the I squared on top will turn into a -1, giving us a positive 30. And the I squared on the bottom will give us a -1, giving us a positive 36. Well, now we can combine it even a little bit further and get 32 plus 7i divided by 37. And we're basically almost done at that point. Remember that you want to take your answer and put it in the form of a complex number so you can clearly see the real part and the imaginary part. In order to do that for this problem, I would change it into 32 divided by 37 plus 7 divided by 37i. So now I can clearly see what the real part of my answer is and the imaginary part. So those are the different ways that you can start combining complex numbers using a little bit of algebra. Now, you may wonder, how come we never see any powers of I, say, larger than a single power? So how come we don't see I squared or I cubed or I to the fourth? Well, the simple answer to this is those larger powers of I can always be simplified to something much easier. In fact, remember when we were working with x squared? Well, that turned into a -1, so it was much nicer. And let's do a few other values, just starting with, like, say that I is equal to I. If you had to deal with I squared, well, that gets simplified to -1. Well, what if you had something like I cubed? What would that turn into? Well, you could kind of use the information that you had before. I cubed can be broken down into I squared times I. Now, of course, I squared is equal to -1, so this turns into -1 times I, or just a -I. So it simplifies to something much nicer without any power on it. Let's give I to the fourth a try. So I to the fourth is equal to I squared times I squared. Both of those are equal to -1. So all of that simplifies to a positive 1. Now you can continue this process for I to the 5th, I to the 6th, and just keep going with much larger powers. And what you keep getting is that it always simplifies back to something easier. In fact, if you take I to the 5th, that simplifies all the way down to just I. If you take I to the 6th power, that simplifies all the way down to -1. And if you eventually look at it a bit, for some of these other higher powers, you get a pattern going on. That you either get I, -1, -I, or 1. These are the only 4 options you're going to get for having a power of I. And that it repeats. Well, you can package all of this into a really nice way to simplify things. If you're looking to simplify a power of I, just take the power and divide it by 4. Then observe what the remainder is. Depending on what the remainder is, you can see what the I simplifies to. So say you have I to the 21st power. Take 21 and divide it by 4. That happens to have a remainder of 1. So I to the 21st power simplifies to just I.